Okay, so we can start now. Right, this is your week 5 tutorial session. So we are having it bit earlier. Today it was supposed to be like after few hours, like as we go with the schedule. Uh, okay, just you could let me know if my audio is clear. Hi Venkata, is my audio clear? Uh, could you able to hear me properly? Uh, Okay, I hope you can hear me. Uh, so today we are going to talk about uh, uh, yeah, quantum particles in some external magnetic field. So today we will be dealing with some time dependent type of quantum systems, and particularly we'll see how when quantum system coupled with external magnetic field, how quantum particles behave and they evolve. So yeah, so so there are some interesting phenomena that that arises when you have this type of quantum system evolving under some magnetic field, right? So first of all, little bit of background to start off with. So so we'll rely on mostly on the spin-off particle. So uh, again, so what is interesting about the spin-off particle? So suppose if you have this spin-off particle at rest, and then you introduce a magnetic field. So so you have a spin-off particle, and then and then you introduce a magnetic field where you have spin-off particle at some point at rest. So let's say the magnetic field is constant and uniform for now. So then, so the spin-off particle that which we are talking about, so it is basically a quantum particle. So it can be an electron or proton. So, and when we are talking about electron protons, so they also do carry charge. So so for a charged particle, like there is something which we are familiar with, is magnetic dipole moment. So if you remember from your like standard electrodynamics course that you had have done in your past, so like in your early graduate days, like I mean just basic electrodynamics. So there you will find that there is something very well-known relation known as gyromagnetic ratio. So so what it says that like if you have a charged particle, or let's say any charged object, and you if you keep it in external magnetic field, then how I mean how the relation of its moment of inertia, and or how the relation of magnetic moment, this magnetic moment and angular momentum like can be shown. So they have a ratio which is very well known, that is q over 2m. So this is very very standard. It also goes back to where how the charges of fundamental particles have been estimated, or the fundamental charge. So yeah, so it's no uh, strange thing about it. So it's like if you have a uh, like mm, like example, like if you take charged particles, charged charged particle, like moving in conducting loop. or some rotating charge sphere. If you have a if you have a sphere full of charges, and if you rotate them, then like uh, like in the external magnetic field, so how I mean uh, basically how the momentum, angular momentum and the magnetic moment can be related. So basically, like in electrodynamics, you do like if you uh, uh, if you talk about uh, magnetic moment, so it is something like you can, if you remember from your electrodynamics course, it is something can be given as R cross J. So where J is your current density, and you integrate it over the volume. So that is that is how you define the magnetic moment. And then and obviously angular momentum is something, whatever the object you have, so based on that object you will have a moment of inertia, and you uh, uh, multiply with its angular velocity, then that is something you are getting, that you used to get angular momentum. So their ratio used to be something q over 2m. So this you can see the magnetic moment is proportional to angular momentum, and with a proportional defector or something that can be scaled by q over 2m. So now, in quantum mechanics, when we are talking about a spin, quantum particles having spin. So quantum particles having spin, they also carry charge at the same time. So again, when you put if you again again we can estimate a magnetic moment associated with them. So any moving charges can be associated with a magnetic moment. So the same way like how we were having rotating charge sphere, or when charges go around a loop we have a magnetic moment, and then we also have angular momentum. Similarly, when quantum particles also have a charge, so they also have a magnetic moment associated with it, and they because they also carry something known as spin, which is similar to the angular momentum. So in quantum mechanics, this is given to be this magnetic moment is also something related to as gamma s, as in the same in the same foot line how we had this mu is related to orbital angular momentum, or not orbital, mu is related to the angular momentum in case of some classical objects. So the same way like how magnetic moment is related to the angular momentum in classical objects with a proportionality going as q over 2m. So that's in the similar way in quantum mechanics, for a quantum particle like electron or proton, its magnetic moment can be related with its spin, with this ratio known as which I was calling it as gyromagnetic ratio earlier. So here we have something similar, which is minus e over m. So just a bit of difference, there is no overall 1 by 2 factor, but it's e over m. So yeah, it's charge over mass ratio. So and then so yeah, now what we are trying to talk about here is like if you have this I mean, if you have this quantum particle, and now you put it inside a magnetic field, or you have a charge, or you have this quantum charged particle, and you introduce a magnetic field here. So then, like uh, even classically. So here as I was talking about, so here there was no magnetic field, any external magnetic field here. So only moving charges, due to which there you have some magnetic moment, which you can estimate from here. But now again, classically, if you again remember, there is something we used to define, a energy, when you put a charge, or when you put a uh, um, yeah some let's say some charged, or a, let's say some conducting loop carrying some charges, and you put in some external magnetic field, then the energy is something given as u equals to minus mu dot v. So this is something, uh, or I think something can be uh, uh, referred to as magnetic potential energy, uh, potential energy. So yeah, so classically this is how the relation was. The same way we will use also the relation for the quantum particle case as well. So so there, the magnetic moment will take the magnetic moment for the quantum particle. So here the magnetic moment would have been this q by 2m times L. But now here the magnetic moment in quantum mechanics, like you will take gamma s. So so then Hamiltonian, which is also like given by the energy. So if this is the energy, then then this Hamiltonian should be expressed as dot product of the magnetic moment and the external magnetic field. So this is your uh, this is your external magnetic field, and so do this one. So yeah, and this external magnetic field is something, let's say, constant magnetic field we are taking, and it is directed along the z direction. So uh, so then how can you completely express this Hamiltonian? So so now so you see the Hamiltonian is given to be this, and the magnetic field is this. Now you want to calculate um, minus mu dot b. So minus mu dot b external. So that is minus gamma b external dot s. B external is b naught k. So you can write the spin vector. You can you can also write the spin vector something as sx, or let's say yeah, I can write the spin vector as something sigma x I k plus sigma y z plus sigma z z. So uh, so what is this? So this sigmas are, if you remember, for a spin half particle, for spin half we have this sigmas are basically the Pauli matrices. So sigma x, sigma y, sigma z are basically or yeah, so they are Pauli matrices. So uh, so in quantum mechanics, this is how you can express your spin vector. So you can write its different components in this sigma x, sigma y, sigma z, and then um, you can use like suppose so yeah, if you take the dot product, so the dot product is basically that your dot product will basically give you h equals to minus mu dot b external. So that means it is minus gamma uh, B external dot S. So that means it is minus gamma B naught sigma Z. So this is what you will have. So yeah, and so this sz head is something written to be sigma Z, because your Hamiltonian is a matrix or a operator. So this sz is that. So yeah, and then you can write this you can write the Pauli matrices if you remember the Pauli matrices. So the sigma x is given as something 0 1 1 0. Sigma z is something given as likewise you have sigma z, which is given as 1 0 0 minus 1, and likewise you have sigma y, which is given as 0 I minus I 0. So right. So but you need only sigma z here. So using sigma z, you can write the uh, yeah, there will be also overall factor of h bar by 2. So there will be h bar by 2 here and also here also. Okay, so yeah, then um, you can write the Hamiltonian finally. So uh, so uh, so you have this Hamiltonian minus gamma uh, b naught over h bar by 2 1 0 0 minus 1. So this is the Hamiltonian you have. And then uh, let me uh, okay. Now for this Hamiltonian, if you see, I can I can write the I can write eigenstates for this Hamiltonian. So when we are talking about eigenstates, so you have this matrix, so you can take the eigenstates. So and the eigenstates for this one is easy to know, because the eigenstates, if you see the matrix, it is just a Pauli matrix. So it's just minus gamma b naught h bar by 2 sigma z. So it's just Pauli matrix sigma z. So if we want to know about the eigenvector of h, so it means eigenvector of sigma z. So I can say eigen vector of h is same as sigma z. uh, so So then the eigenvectors are basically um, I can write, let's say, eigenvectors. It will have two eigenvectors. One is chi plus, which is 1 0, and it has eigenvalue. So let's say eigenvalue. If you calculate the eigenvalue, you will find, let's say, I'm writing this eigenvalue. Let's say lambda plus is uh, minus gamma p naught h bar over 2, and it will have another eigenvector that is 0 1. So the basically these are your up state and down state, which we have discussed a lot during our last session. And so yeah, so while we were doing quantum information, the same way you will also have eigenvalue lambda minus, which is gamma b naught h bar. This is plus by 2. Yeah, gamma b naught plus gamma b naught h bar by 2. And now, since as we were talking about this, what happens to the spin when you put them in the external magnetic field. So spin in the sense, the quantum particle which is having a spin and also carrying a charge. Now here we are seeing what happens if it is kept in an external magnetic field, and the external magnetic field here, it happens to be a constant magnetic field. So and then if you let the system to evolve, then how things will unfold. So in order to know like how the system will evolve, so we will use time dependent Schrodinger equation. So uh, from yeah from time dependent Schrodinger equation, like we can have I h bar uh, del chi by del t equals to h chi. So what is chi? So chi is some initial state. Uh, 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 so where chi is some not initial state, some uh, uh, what we can say, it is some state which can be uh, in linear combination of upstate and downstate. So that is like, for example, if you like when we talk about the other systems as well, like the infinite well and harmonic oscillators. So at any given point of time, if we want to know what is the state of the system, so it is basically the linear combination of its eigenstates. So here also, as we have seen, the Hamiltonian is something which is exactly same as the sigma z, the spin state basically. So it's or it's like at any point of time t, its state would be something linear combination of this upstate and downstate. So and it will have some coefficients. And for now, if we say the coefficients are just simply um, let's say uh, yeah, let's say the coefficients are something a and b. I can write this a chi plus exponential minus I lambda plus uh, let me write this lambda plus and lambda minus as something e plus and e minus. So let me write this as e plus, then t over h bar. Then I will have another term that is, and its coefficient, let's say b chi minus exponential minus I e minus t over h bar. So yeah, so this is something, if I tell you that um, suppose if I have a like just to remind you, like if I want to evolve some quantum state, let's say uh, del t h psi, and let's say the initial state psi, psi 0 is the initial state. It is uh, initial state is something a phi 1 plus b phi 2, where phi 1 and phi 2 are eigenstates of H. Then I can, yeah, then from here I can write psi of t is exponential minus I h over h bar t, psi 0. Then this I can write it as exponential of minus I h over h bar t, uh, a phi 1 plus b phi 2. And so when this acts on phi 1, so it will give me, since uh, phi 1 phi 2 are eigenstates of H, so this means H phi 1 will basically give me E1 phi 1, and H phi 2 will basically give me E2 phi 2. So with that knowledge, I can write this as, uh, yeah, I can just simply write this as psi of t as directly as some coefficient exponential minus I e1 over h bar t, phi 1 plus b exponential, again minus I e2 over h bar t phi 2. So yeah, yeah, so this is because since these are eigenstates, so I can write this even if I take some exponential like operator. So if this is true, then for an operator this is also true, that if I take something exponential of h and phi 1, then it will also give me some exponential of e1 and phi 1. So yeah, so with that, like, I can write this psi t to be this. So same way I have written with that uh, like idea. We also have in our um, spin in our system of spin in the external magnetic field to be of this form. So that is why we have written uh, uh, chi plus and chi minus, which are the two given states like phi 1 and phi 2, as I have said just right now. Same way they are multiplied with the exponential term, because this is some state at some time t, so there would be some linear combination, and this is the overall evolution factor which they will have. Yeah, and with that they will have some coefficients a and b, so this will be determined by knowing the initial conditions precisely. So yeah, we'll see now. Yeah, so now so this is just some additional piece of thing to make you remember. So okay, now getting back, so as I said, like we found chi of t. So chi of t is basically, it is again uh, yeah, yeah. So chi of t is a exponential I gamma b naught t over 2, and b exponential minus I gamma b naught t over 2. So I am writing down exactly what is e plus and E minus. So from here, uh, okay, then then we have to know like what is chi at zero. So chi at zero is basically a and b. So these are coefficients, and uh, and this coefficient, like for now, we can take something of this combination. Let's com- let's take a equals to something cos alpha by 2, and b equals to something sine alpha by 2, and this alpha is some angle which we will know in some moment. So yeah, uh, like why I can take this in this form, like you can take even more general form, something even uh, something of the complex form, like something, I think some similar doubt was there in the like in the questionnaire forum. So somebody was trying to know. So yeah, but for now, like we're keeping it something a bit simple, where we see that both a and b, the coefficients, they depend on some parameter alpha, which is key here, uh, 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 what we are trying to see at the end. So and this alpha is yeah, some angle. So and this is also true because I can assure that, like if I take one is something cosine and the other is sine, then the total probability is also conserved. So what I mean is the uh, if I chi 0 is normalized. So if I take chi 0, uh, a dagger chi 0, so it will give me uh, 1. Yeah, so this is or otherwise, so a square plus magnitude square is 1, right? Then so we have this chi 0, and so from this we've let's say we found this a and b. So a and b is something now fixed, so we can write chi of t as cos alpha by 2 exponential I gamma b naught t by 2, and same thing sine alpha by 2 exponential minus I gamma b naught t by 2. Yeah, any questions you can ask, like anyone, uh, do you have any problem, anything, um, Priyanka or
No,
Venkat?
sir.
Okay, so
No, sir, not yet.
okay, okay, yeah. So yeah, fine. So then um, okay, so now like we found out the state of the quantum particle with having spin half, or the spin half quantum particle, which also carries a charge, and which is under some external magnetic field, and it will evolve in some following state. So the state at any given point of time t, for that quantum particle, can be represented by this state. So right. So now suppose in this state, like at some time t, we want to know, let's say uh, at some time t, uh, what are the expectation uh, values of s- Sx, Sy, and Sz. So the quantum particle, which has a spin, so it has the spin will have three components. So for all the three components, like we want to estimate what is their expectation value at some time t. So then for expectation value, we use a state to calculate the expectation value. So that state, like here, if we want to know the expectation value at some time t, then we will use this state. So the state at some time t. So so suppose we want to know expectation of Sx, then it will be chi of t. So chi of t Sx chi of t. Then uh, uh, yeah, so then it is so if you use this chi dagger t, so this is, if this is if this is chi t, which is a column vector, so it is just basically a row vector. You will have that, and then you use sx. So sx is something given as h bar over 2 uh, 0 1 1 0, and then again you have uh, chi of t. So yeah, so from here you will get sx equals to uh, if you multiply all this, if you do this matrix computation, this matrix multiplication, you will get h bar by 2 sine alpha cos gamma b naught t. In the same way, if you do sy, you will get h bar 2 again sine alpha, but sine gamma b naught t. Uh, yeah, so right. So remember, like this cos gamma b naught t and sine gamma b naught t. So they are essentially coming from here. So if I write something exponential I gamma b naught t, because this is b naught t by 2, then uh, plus exponential minus I gamma b naught t by 2 over 2. This is basically uh, cos of gamma b naught t by 2. Basically it will have so this is cos of gamma b naught t. Okay, so yeah, so similarly you will have some relation in sy as well. Then right, then you can do the same calculation for sz as well, and uh, sz will give you h bar by 2 cos alpha. Now what we have here is like so to understand this, like how this spin basically is varying, it is in the following way. So suppose if we draw a spin orientation, like how this spin is actually evolving under this external magnetic field. So what we have is, so we have some magnetic field, as we have seen, b naught uh, along z direction, z cap. Then so right, and so let's say this is y, and uh, so, and this is your spin vector. So if I am like representing something in some coordinate axis frame, so I should use this expectation, because like without expectation it won't make sense, because it is some linear combination of state. But if we are talking about some expectation, it is some particular value. So that is why I can plot them. So what is happening if this is z is along this side, so that means you can understand this is alpha is something measured from z. So it is like this spin vector at time t, uh, at time so yeah, so this means at time t, your s vector is uh, tilted by alpha is tilted by alpha angle with z axis. And then it is not just tilted, you will find that this actually it is something precessing, meaning it actually like so this is something this is actually something rotating this, or otherwise this is something known as precessing. So this omega is basically your gamma b naught. This is the frequency with it is uh, or basically the angular frequency with it is rotating. So this is known as your Larmor frequency. uh, or also this precession frequency, or you can also say this is the gyromagnetic frequency. uh, Gyro uh, magnetic frequency. Okay. So yeah, so this is the point which I was trying to make. So this is something not very usual. Like if you take a like a um, as we were talking about the I mean classical uh, angular momentum, or the classical objects carrying charges, and also where they also obey some gyromagnetic ratio, this QO2M. So when we keep them in some external field, so they do not show any, I mean, this unconventional type of precision. But in quantum mechanics, when you have the spin in some external magnetic field, so they precess. So they precess with this. frequency, which is gamma b naught, and then this alpha is the angle with which they are additionally tilted. So they remain tilted, and they uh, uh, with that they also presses about. So yeah. So any questions here? Any doubts or something not clear? You can ask. Um, so that is just the basic idea what you can expect if you have a quantum particle having some spin and charge, and you place them in some external magnetic field. So here we have considered to be a constant magnetic field. Then you will find this kind of precision phenomena. So yeah, okay. So we can follow up some quick related questions here. So right. So if you have a spin particle with gyromagnetic ratio gamma, and again you introduce a magnetic field which is constant magnetic field, and it precises with Lamer frequency omega naught equals to gamma b naught. So with just what we have seen, now a small transverse radio frequency magnetic field is also introduced. Uh, is turned down, so the total field is so now. So initially, it was like uh, you had some magnetic field which is b naught kk, and due to which your spin vector was actually uh, precessing. So right, it was. So this thing was. So this thing is precessing your spin vector, but now you also have additional two components of magnetic field. So on top of this, you also have uh, like some like by component and also bx component. So your total, then what will happen to your yeah. So yeah, okay. So then your total magnetic field is this. So then first you have to see what is your Hamiltonian in this case. So again, if you remember, as we have started out, the Hamiltonian was something given to be minus gamma uh, b dot s, uh, or basically your Hamiltonian was uh, mu dot b minus mu dot b. So yeah, so so right here. So that means your mu is in quantum mechanics, as we discussed, it is minus gamma s. Gamma is a gyromagnetic type ratio, which is E over m, uh, just like in classical we have. So yeah, so here h is minus gamma b dot s. Then just again you take the dot product, so then component wise you will have something this bx sx plus by sy plus bz sj. Then uh, yeah, then Again, if you remember your Pauli matrices, your Sx can be written down as h bar by 2 0 1 1 0. Sy is uh, h bar by 2 0 minus I 0, and SC. So now using them, you can write down, and bx by bz is given in your question. So you can write minus gamma h bar by 2 bx, uh, yeah, right, bx 0 1 1 0 plus by sy, so which is 0 minus 1 I 0 minus I 0, and uh, bz 1 0 0 minus 1. Okay, then yeah, you if you use the explicit magnetic field component expression, that is uh, so if you see, uh, bz is b naught, the z component b naught k cap, so that is why you have b naught here. And same way, if you write down the other, so it will be b bx, uh, so so here you basically have bx minus I by, so that is basically uh, that will give you uh, b rf cos omega t plus I sin omega t. And then same thing, similarly you can have drf cos omega t minus I sin omega t, and minus b0. Now you can see this, you can write it as exponential I omega t, or and same this you can write this exponential minus I omega t. Yeah, so this is your Hamiltonian. So okay, so then yeah, any problem you can let me know. So now so if the state again in this Hamiltonian is some at time t is given by a of t and b of t, likewise how we have seen, we have calculated the state in the previous case. So but that won't be the state here, because earlier we had just constant magnetic field, but here our magnetic field is time dependent, so we have to properly solve the time dependent Schrodinger equation and then estimate the states exactly. So here, let's say is the spin state at some time t, show that derivative of a is given to be this, and derivative of b is this, and furthermore there is some relation that gamma times brf is omega. So we have to show, like to show this, we first have to understand what is exactly a of t and b of t. But essentially we can see here, without knowing them we can also try to find out. So suppose if we directly use time dependent Schrodinger equation, from time dependent Schrodinger equation, we have IH bar del chi, or del t equals to h chi. Then you can write down IH bar del over del t, a of t, b of t. Then h as we just found out, which is minus gamma h bar by 2. First element is b naught and the other is brf, exponential I omega t, and we have brf exponential minus I omega t and minus b naught, then a of t and b of t. Yeah, then if you take the derivative, so it's simply going to give you, so this I h bar a dot equals to minus gamma h bar over 2, uh, b naught b, plus, sorry, it is b naught uh, a plus brf exponential I omega t. This is b. So this a dot is basically I over uh, I over 2, and then using gamma brf is omega, which is something given in the question itself, and then also writing down gamma times b naught, which is your Larmor frequency. uh, Larmor frequency. So I can have uh, uh, right, omega naught a plus omega exponential I omega t b. So yeah, this is your uh, a dot, and same way you can also write down what is b dot. So which is yeah, I over 2 omega. I think there is just will be a minus omega exponential a minus omega naught b. Okay. So yeah, same way you can see what will be b dot. So this is simply coming from the time dependent Schrodinger equation. Nothing much to do here. So yeah. So any problem you can let me know if you are not able to follow somewhere.
Hello, sir.
Yeah.
Could you tell what book you follow?
For the, I mean, particularly for this topic, or in general,
For
because
this course, like for the these sessions, from what book you teach and like
for
what book
for
you follow?
this for this one, like I generally see, I mean, this I mean, Griffiths is the, like would be the easier one, and also Jet Li you can see, would be easier. And then if you want to go a little bit more standard, then you can follow Sakurai and these books. So yeah, like these 2 3 books is enough to like go through, like, but start with the easier ones and then go more like a bit more detailed. So in the other advanced books or something, like Cohen Thanos is also one good. But yeah, like for this one you can see Griffiths or Jet Li. So yeah, and there are also other topics, like for example quantum inform, like last time which we were talking um, about the quantum information. So for, like, I didn't follow any proper book for that topic. Like I have seen some like lecture notes, like if you know there are some popular lecture notes by David Tong, so Professor David Tong. So there also you find some interesting details and information. So last time I was following that. So it's like so different topics you can find from different sources, which is more better than sticking to only one book, because one book may not cover all the details of all the topics. Sometimes one topic could be given in very incredible way, and the other topic may have some sort of shortcomings. I mean, may not be very explanatory itself, but yeah, you can have some significant information from there as well. So yeah, uh, yeah, you were talking especially on this topic, right? Or
I think
uh,
might
uh,
be.
sorry, like your voice was not clear. Uh, Sorry, like I'm not able to hear you properly. Uh,
Hello.
yeah, yeah, yeah.
In general, teach here on this session what you follow.
In general, which book you want to follow?
No, like I was asking what book you follow for teaching here in these sessions, problem solving sessions.
Actually, again, I'm not finding your voice properly clear. Like, could you just quickly write it down, your question? I mean, initially your voice was clear, but now all of a sudden, uh, uh, oh, okay. Yeah, yeah. So as I said, like these are the books like I generally go through. Like as I said, like I sometimes I like follow one or two things from the Griffiths and Jet Li, and some lecture notes, as I said, David Tong, and sometimes like some interesting things are given in like Sakurai as well. So from all this like sources, like I try to give you a impression of what kind of concepts and related topics can be. So yeah, so that is how like I have done, like for example, core instance, I think I have followed something maybe from Jet Li. Yeah. So likewise, I've been doing this. Yeah. Okay. Yeah. So if there's any other question anymore, like you can let me know. uh, okay. Okay, if not, we can see the next one. So the next thing here is for the general solution of A of t and B of t. So if we solve the Schrodinger equation with proper initial values, which is uh, like denoted by A naught B naught, uh, then the solutions are given to be this, the the exact solutions. So A of t is this, and the B of t is this, and then there is this frequency again, um, which is uh, this is basically, I think, the NMR frequency. uh, okay. So then like we have to show the this uh, Yeah, so we have to show exactly this a of t is a solution here. So like in general, like how do you have started this? So suppose like if this is given, um, like for example, this is the Hamiltonian which we started with. So this is the Hamiltonian. Uh, where did it go? So yeah, so our system is this. So this is the Hamiltonian, and then we said under this Hamiltonian. So this is so under this Hamiltonian, like we can specify the state of the spin of particle, which is in this magnetic field uh, by this. A quantum state. So this is the state. So if if we say that this is the state with which it evolves under this Hamiltonian H, then like how we can exactly know what is A and B. So to know that, like we have to start, we have to use this Schrodinger equation. So yeah, from Schrodinger equation we got this a dot and b dot expression. So and now if we solve this a dot and b dot with proper initial conditions, then we can know what will be a and b. So if we see the process, like it would be something like from time dependent Schrodinger equation, we can write del chi over del t I s bar and h chi, right? And then from there, like we found uh, a dot uh, equals to I by 2 omega exponential I omega t b plus omega naught a. So this is as we have seen at the starting of this problem. So omega exponential minus I omega t a minus omega naught b. And now if you see, uh, these two are coupled uh, uh, ordinary differential equation, coupled ODE. So if these are your coupled ordinary differential equation, and we want to know what is a of t and what is b of t, then the first thing you have to do is uh, first we have to decouple them. So so if we want to for example, if we take the if we take another derivative of this expression, so it will have something a double dot equals to it would be I by 2 omega, then again it would be I omega exponential I omega t, then uh, right, uh, b, then again I will have omega exponential I omega t b dot plus I will have omega naught a dot. So I would get something of this type of expression. And then if I use uh, uh, let me see, yeah, so then if I use the expression of b dot and also a dot from here, then like uh, I can get a expression fully. Like I have to first I have from here I have to fully construct a expression, or basically the differential equation fully consisting of a dot, a dot, a double dot, a dot, and a. Same way, I have to also get an expression having only uh, um, b dependent variable. So like something b dot, and again something b. So if I get so that is what I mean by decoupling the coupled ordinary differential equation. So it's basically you take the derivative and then you use the expression of a dot and b dot again once more in the a double dot derivative equation. Then you will find that you can decouple it, like everything. So what happens, everything in this differential equation will convert in terms of a double dot, a dot, and a. Nothing will remain in b. So that is what I mean by decoupling. So yeah. So then finally you can solve finally from a double dot, from equation you can get a of t, and from the second you can have b of t. So this is the way to do. um, yeah. So it's basically you have to solve these two type of equation: a double dot, b a dot, plus c a equals to 0. This is one type of differential equation you have to solve, and you have to solve uh, can be, yeah, again something a prime b double dot plus b prime b dot plus c prime b equals to 0. So yeah, from here you can get a of t, and from here you get b of t. So yeah, but now without going any of this right now, because you will find this to be quite a long process. So we can get a way around even more nicely, and probably even more quickly. So if we just simply start out, let's say uh, uh, taking uh, time derivative of the given expression uh, of a of t. So a of t is already like given in the problem. So just we first take the time derivative of this a of t. So what it will give us a dot. So you have to take the time derivative of this. So yeah. So from first you will get uh, cos omega t is derivative minus sign, so it's minus omega prime a 0 sine omega prime t by 2. Then we'll have plus I omega prime from this second, uh, right. A naught, uh, omega naught minus omega, uh, plus b naught omega. Then derivative of sine omega prime t by 2 is omega prime 2 cos of omega prime t over 2. And then yeah, this is exponential I omega t over 2. Then plus uh, yeah, then plus the like whole thing, I omega by 2, but this is something is a of t. So which means a dot is basically your uh, I can write it down as uh, I by 2 exponential. Uh, so here I mean this is I omega t, I omega t by 2, and I omega by 2. So after derivative, you get the I omega by 2 factor. So then I am telling that this whole thing becomes your A of t. So, right. Okay, so or otherwise you can write in the following way. So just the derivative. So there is nothing very surprising happening here. So like it's a straightforward uh, derivative. So omega a naught cos omega prime t by 2 plus I omega over omega prime a naught omega minus omega omega naught omega plus b naught omega uh, sine omega t over 2. Then again you have one more term which is I omega prime uh, a naught sine omega prime t by 2 plus omega naught or it is a naught omega naught minus omega plus b naught omega cos omega prime t by 2. So this is whole thing. Yeah. So anything, anywhere, if you lost somewhere something not clear, please you can uh, let me know. So it's just simply I have taken the overall factor of exponential, and then uh, inside it there are three terms. So any problem here? Anything? Anything if you lost somewhere or okay. So uh, till here you have this. Uh, okay, fine. So then you also know what is like in the previous like question we also seen what is a dot like from the Schrodinger from the time dependent Schrodinger equation. So from time dependent Schrodinger equation we also had what is a dot to be, which is I by 2 omega exponential I omega t b plus omega naught a. So again, now if this is from Schrodinger equation, this was the expression. Then this should be equal to the one which we have found out this long expression here. So then, yeah. So we can now write uh, I by 2 omega plus omega naught a. Then Yeah, then this is equal to this whole thing. Okay, so this is equal to this whole thing, and then so from here, if you collect um, like from here, like collect cos omega prime t by 2 terms. So if you do that, uh, so that will be I omega by omega prime. Uh, so then that is a naught omega naught minus omega plus b naught omega plus I omega prime a naught. Uh, that is equals to I omega over omega prime b naught omega minus omega naught plus uh, a naught omega plus I omega naught omega prime a naught omega minus omega naught omega plus b naught uh, big omega, and then right, and then so if I take everything on the left, if I simplify this more, it would give me a naught omega omega naught minus omega square plus omega prime square minus omega square minus omega naught square plus omega naught omega. And now if you see uh, what would be this expression, so um, okay, so now if you see this like uh, a naught is not equals to 0, remember, and so that means if anything has to be 0, then this has to be 0. So yeah, okay, so if this has to be 0, like if you remember in the problem, it has said that these are the only solutions. If these are the uh, uh, exact form of the solutions, then they must obey this frequency relation, which is your basically the NMR frequency. So yeah, so this is your Rabi frequency. Uh, so this Rabi frequency is, if you use this here in this expression, uh, like this is true only if omega prime is defined to be omega minus omega naught square plus omega naught square. Yeah. So then this proves that like this has to be the solution which is given in the problem a of t. And same way, like you can also show for b of t, and where again you will find a similar expression where you have to substitute this, and upon substituting you can find what is d of t. So it's basically we are taking the derivative of a dot, or we are taking the derivative of a and b, and we also know, and then we are equating with the expression of a dot and b dot, which we already had before from the time dependent Schrodinger equation. So that is what we are trying to do here. So yeah, if not clear, like please ask me again if something somewhere not properly understood. Okay, if it's fine, then we can quickly see the other one. So um, the next we have is, if the particle starts out with spin, uh, if the particle starts out with a spin up, like then a0 is 1 and b0 is given to be 0. Find the probability of transition to spin down as a function of time. So what it is uh, asking here is following. So it is telling that if it starts as spin up and then finally it goes down as spin down. So here spin up denotes the 1 0 state, 1 0, and spin down is your uh, yeah. uh, there is question. Hello. uh,
Sir, can I, is there a,
uh,
sir, whatever you explain, but I can't understand. So
which part, like which one?
this one, sir, I tried to understand, but it is
uh, uh, like
difficult to understand.
I mean, this one means like from the starting or where?
Yeah, starting.
uh,
Okay, but after that, can you send this the video lecture?
yeah, so this video lectures and the whole details, I mean, the
Have-
including the presentation notes, like everything is shared with you, like for all the weeks, so you can access it through your portal. So if you can find through your portal, so you can get them. So
Okay, sir. Thank
yeah,
you, sir.
so like, were you there like from the starting, or you joined in the middle?
Join middle.
Okay, okay. So try to see from the starting, like what is going. Then if there is any problem, like let me know.
Okay, sir. Okay, sir.
Yeah, yeah. So next we were trying to know, like we have to calculate this probability. So yeah, so the down state is actually it means 0 1 state. So uh, yeah, at uh, t equals to 0, the spin state, like it would be something a0 b0. So uh, a0 is already also said in the question, it is something upstate, 1 0. uh, that means then if we evolve this into some, so if we start out with this chi 0, then if we evolve this using Schrodinger equation, like this state will evolve if we let the system to go. Then it will be something uh, a of t and b of t. So So what we know here is like we know the initial condition. So uh, if if it is telling if the particle starts out with spin now, so this means this is your initial condition. So initial condition. So then uh, but then your question was find the probability of a transition to spin down. So like this is at t equals to 0, then at t equals to t, you will have something chi of t, and then let's say this is your final time. This is t equals to tf. At final time, you want to have this uh, at final time you want to have this spin down. So that means your probability, you can write your probability as uh, spin down state, which is and chi of t. You have to take the inner product square of chi of t and the final state, that is spin down. So this thing can now be written down as 0 1 and a of t and b of t. And now this is basically your um, b of t mod square, or that is basically b of t complex conjugate b of t. So now if you see your b of t expression is already given here. uh, so this is your b of t expression. Right, so using this b of t expression, so like your a0, like from initial condition you have uh, a0 equals to 1, b0 equals to 0. uh, like this b of t, let me check if this is uh, just give me a moment, let me check the expression once again. uh, yeah, so this expression is slightly incorrect. It will be b naught. Yeah, now it is fine. So it is b naught. Yeah, so now if you put a0 equals to 1 and b naught equals to 0, so that means this thing will go to 0 and this term will also go to 0. Yeah, and you put a0 equals to 1, so this term is basically omega. So from here you can get what is b of t, and then from b of t you can show that, like you can calculate, it would be something omega by omega prime square sine square omega prime t by 2. So yeah, so basically you will see that your uh, this is your what probability will become, probability at time t, the probability to get your spin down state from chi t, from chi t to spin down state. This is your probability. So yeah, so your b of t is basically it would be something I by I omega prime sine omega prime t by 2 exponential minus I omega t by 2. Yeah, so this is your basically your b of t. Okay, so yeah, so any question here you can like let me know, anything not clear. So okay, so if not, like we can quickly see another question of similar type. So yeah, then we have this. Yeah, again we have a electron which is spin half at rest in an oscillating magnetic field, and this time the magnetic field is given to be this, which is only having one component, which is b naught cos omega t, a time dependent magnetic field. Then again calculate the Hamiltonian. So again what we've been doing from the beginning, so that is what we have to do here. So that is minus mu dot b is the expression for magnetic field of is the expression of Hamiltonian for the spin of particle in this external magnetic field. So so this is minus gamma b dot s, since mu is your minus gamma s. So then again this becomes h is minus gamma bz sg, where bz is basically minus gamma b naught cos omega t sg. Uh, so yeah, then like in matrix form you can write it as uh, 1 0 0 minus 1. Okay, so this is your Hamiltonian. The same way how we are writing down Hamiltonian. This is again another simple way to do, like it's only one component, and so you have this PZSG only. You are contributing term in the Hamiltonian. So yeah, and then next here it is said that like at t equals to 0 your electron had spin up state, but remember this time spin up state is with respect to x-axis, x component of the spin. So it means that you have this spin operator for the spin half state, which is 0 1 1 0. So it has two eigenvectors, like its eigenvectors are uh, if I denote these eigenvectors by sigma x, then it has two eigenvectors, which is given as 1 over root 2 1 1, and 1 over root 2 1 minus 1. So so this is spin up for the this is known as spin up state, and this is known as spin down state. So this is not the usual spin up down state like which we used to write down the spin up state, spin up spin down state uh, in the sz basis. So this is in we call this as sx basis, uh, spin x component basis. So like in SZ basis, our usual relation used to work. Like for example, in SZ basis, we were writing 1001, where sigma z, where these were the uh, eigenvectors of 100 minus 1. So there is overall h bar by 2 factor which I am missing out, but to show the eigenvectors, it is enough to just show the matrix. So yeah, uh, let me write Sx equals to h bar by 2. Yeah, okay. So it is given that like your initial state is spin up state, which means this is your initial state. Uh, Initial state. So that means uh, chi at 0 is your initial state. Let me write this as chi 0, which is 1 over root 2 1 1. So that this means your a0 equals to a0 and b0 both equals to 1 over square root 2. So then your chi of t at some time t is again something would be a of t and b of t. Uh, and chi 0 is a0 is 1 over square root 2 1 1. So then from Schrodinger equation, we have to find out what is chi of t. So to find out the chi of t, which means we have to find out what is a of t and b of t. So to find out what is a of t, b of t, again we will use Schrodinger equation. So then we have to solve the differential equation, because from Schrodinger equation we'll get the derivative of a and b, and yeah, something of the form of differential equation of in a and b. So this is like from time dependent, we have to use time dependent Schrodinger equation, because again we have a time dependent Hamiltonian system. From time dependent Schrodinger equation, we have IH bar uh, del chi over del t equals to h chi. So this is IH bar a dot b dot, a dot and b dot equals to h chi. So h is given h as we found out in previously to be this. So this is your h. So minus gamma b naught h bar by 2 cos omega t 100 minus 1 a and b. So if you see your expression will become a dot is I gamma b naught by 2 cos omega t a, and then you have b dot of t is minus I gamma b naught by 2 cos omega t b. So now if you see we have two equation, equation 1, equation 2, uh, like which are not coupled this time. So now we can simply solve them, like from like solving one will give uh, like you can just simply do the variable separation and solve it, which you have to integrate basically. So I gamma b naught by 2 cos omega t dt. So And remember the initial condition a of 0 is or a naught is 1 over square root 2. So here you have log of a I gamma b naught by 2, the overall factor, and then cos omega t integration is sine of omega t over omega. Then you have this integrating constant. So then, yeah, your a of t something would become using the uh, like even using the value of a0, the initial condition, you will get this c equals to uh, uh, log of 1 over square root 2, so ln of 1 over square root 2. So then finally you will have something 1 over square root 2 uh, exponential I gamma b naught over 2 omega sine omega t. So again, something again you can do check for the b of t. So which will be 1 over square root 2. This will be exponential of minus I gamma omega naught b naught over 2 omega sine omega t again. So yeah, so then chi of t is finally something 1 over square root 2 exponential I gamma b naught over 2 omega sine omega t, and again this would be minus gamma b naught over 2 omega sine omega t. Yeah, so this will be your chi of t. Uh, yeah, just we have last one more problem. So anything, if anything not clear, you can let me know now before doing the last one, or if everything's fine, we can quickly see the last problem here. So okay, if there is no question here, uh, okay, so finally we have this question. So find the probability of getting minus h bar by 2 when sx is measured after time t. So again, we have to calculate minus h bar by 2. This means this corresponds to spin down state in x basis, because we are doing this whole thing in sx basis. So which means we have to like the final state is this. This is the final state. So final state. So then that means we have to calculate the probability. The probability is then can be written down as this is the final state in x is conjugate you have to take, because that is your final state, and the inner product is will be with this with the chi of t state, and you take magnitude square. So then yeah, and chi of t again, with chi of t which we found out here, you have to use this one chi of t. So let me write down chi of t again. So chi of t is this thing 1 over square root 2 uh, exponential I gamma b naught over 2 omega sine omega t. Then again you have exponential of minus I gamma b naught over 2 omega sine omega t. So this is your chi of t. Yeah, so if you use this in probability, So you have 1 over square root 2, 1 and minus 1, and then this chi of t. Yeah, if you do that, so you will get something. Uh, uh, there is also 1 over square root 2 here, so this will become 1 by 2, and you will have exponential I gamma b naught over 2 omega sine omega t minus exponential minus I gamma b over 2 omega sine omega t, and this whole thing you have to take the magnitude square. So this is something. So this thing basically it follows something like sine x in terms of Euler relation is exponential ix minus exponential minus ix over 2y. So so yeah. So using that, like we can write uh, uh, this will be I of sine gamma b naught over 2 omega sine omega t square. So yeah, so then finally you have the probability, which is sine square gamma b naught over 2 omega sine omega t. So yeah, so this is what finally you will have. Okay, so yeah, so this is the probability of going from yeah, so this is the probability of going from chi of t to spin down state in x basis. So yeah, so any problem here, any question, anything, or any other questions also, like from the assignment or the course that you are doing, like it's already over the I mean, I think week 6 course lectures are also out, and probably after 2 or 3 more weeks, these things would be like almost done for you, and then and also most of you have to also appear for a test. So I hope like you're trying to clear things right from now. So like clear your understanding like before you go for the test, and yeah, so please try to see like follow the assignments properly at first, and yeah, and also the lecture videos is needed. Without like following the lecture videos, you won't be able to like solve the assignments. So and yeah, so there's still more questions, like if you need still more understanding, then you can follow whatever discussion what we are doing, and also come here to discuss and clear your or to resolve your other issues. If you are not following anywhere, or anything, any other issues with the course, so you are welcome to clarify here. So we will try to sort it out. Um, so yeah, so this basically ends your week 5 problem solving session, and so we'll have few more, and so we are almost towards the end, and uh, so try to like finish up things as fast you can. Um, so okay, so any questions or anything more? Okay, so today this is all about your discussion on time dependent magnetic fields. Sorry, time dependent Hamiltonian system in quantum mechanics. Like there will be more time dependent things like which we will see in the perturbation topic. Um, but this is all about mostly your quantum spin dynamics in the external magnetic field. So, which happens to be time dependent in nature, and thereby you had time dependent Hamiltonian systems, and we mostly uh, do things by solving the time dependent Schrodinger equation. So here, unlike the other time independent systems which we've been doing, like where we have a potential at, from the starting, and we put it inside the time independent Schrodinger equation, and then we used to get the solutions and states and their eigenstates. But here, as we have seen, for particularly in the context of spin half systems, this is all time dependent system where we have not used any potential. We started out with exact Hamiltonian, or the Hamiltonian expression, which is always given in like throughout, as we found, which is found to be minus dot product of magnetic moment and the magnetic field, external magnetic field, and that external magnetic field happens to be time dependent. So from that time dependent Hamiltonian system, so like we begin with Schrodinger equation for the time dependent case, and we solve the Schrodinger equation to get the states. Uh, so yeah, so okay, if there's no question, we'll see more on the a few more weeks to like to have this discussion in this problem solving sessions. So yeah, so we'll see again. If there's no question, we can stop here. We can end right here. So yeah, thank you and bye.